Today, I'm going to be sharing with you some of the research that we've done over the past 8-10 years with the fire service and for the fire service. And the purpose of the research has been to develop data primarily, and also to develop a base of knowledge that the fire service can use to improve their own safety. It gives you an idea as to maybe a little bit of perspective on the U.S. fire service a little bit. U.S. fire service is about 1 million firefighters, so it's a pretty large group of individuals, and they serve about 30,000 fire departments. But as you can see, a lot of the fire departments are either volunteer or mostly volunteer fire departments, and they protect about 40% of the population. And I think that's where some of the challenge arises, because in terms of training, there is no really central base for training for firefighters, partly because they've got so many firefighters who belong to volunteer, mostly volunteer service. And we have a pretty large fire problem in the US. Approximately 1.5 million fires that results in about 3,500 deaths, lots of injuries, and very large property loss. And an average of fire department response to fire every 22 seconds. So it's a pretty busy department. Fire departments are fairly busy in fighting fires. If I compare the results with what you have in Europe, the fire burden in Europe is actually significantly lower than what we have in the US. So it's something we need to learn from what Europe is doing. And I think that's why this meeting and discussion with the Institute here could be very valuable for us to take back some of the learnings that you have developed out here in the country. One nice thing about the fire statistic is that it's slowly declining. Over the last 30 years, we've seen a decline of about 53%. That would typically be a good thing. It's a welcome thing that we are reducing the fire burden through engineering and through science primarily, and also through outreach, education, etc. But the problem is that the firefighter injuries and deaths have really increased considerably over the same time period. So what has changed? Or what is missing here is the question that we had about 10 years ago. And we felt that in order for us to address that question, we had to gain a better appreciation of what the fire service does. And one of the things that we have found out is that maybe there is a new thinking required in the fire service in terms of the type of training they get, especially in understanding fire behavior, in the type of structures that they have to fight fires in, fire progression, and then also specifically, how has the fire ground changed? How have the realities of the types of fire they're fighting changed over this year? And that can probably explain the increase in number of injuries and deaths that we have noticed. UL is actually a very good fit for this research, primarily for a number of reasons. One of the major one, I believe, is the fact that what we do in research for firefighters fits extremely well with our own mission of promoting safety, safe living working environments. But also historically, I think it's a really very good fit. UL's first office in 1894 was co-located in a fire station. And our founder, William Henry Merrill, used to at times go with the fire service at the fire scenes to get first-hand experience and get information regarding the specifics of causes of some of the fires. And then over the years, we developed a fair amount of technical expertise. We have, as Gus mentioned yesterday, fire has been our core area of research and investigation for more than 100 years. And with that comes with expertise in things like building codes, product standards, testing, specific electrical and fire hazards, and then also development of some unique testing capabilities that allows us to test and develop data that becomes relevant for the fire service and useful for the fire service to integrate that into their new thinking. So I was going to talk to you something about the work that we've done using our unique facilities here in Underwriters Labaratories. Here are some of the projects that we have worked on over the last 8 years, since 2005. And we're very fortunate to get support from the US government, primarily Department of Homeland Security, in funding all these projects. And we continue getting the support because I think we're doing some good work that's being recognized by the fire service. But the themes have been very similar. All the projects, to some extent, involve education and training, either as a focus of the research or as an outcome of the research work. All of them deal with some kind of hazards that are very specific to the firefighters. Specifically, we worked on a project in 2007 that looked at firefighter exposure to smoke particles. And I'll be discussing a little bit more about that today in my presentation. And ever so often, you get a new thing that the firefighters want to use. For example, in the US, there was a push for using Class A extinguishing foams. And the question was, how effective are they? Are they specific to how firefighters fight fires with the amount of water they use? And in this particular case, we found that it's not really very effective, specifically with the 2-inch and 4-inch hose lines they use. It's just a lot of water. You don't need any other extinguishing agent to add to the power of suppression of those fires. And then we looked at various tactics. These are the projects I think you probably must be most familiar with. I don't know how many of you have seen our reports on ventilation, if you can raise your hands. So quite a few have looked at it. That's very impressive. And this work continues. The newest project will be looking into use of positive pressure ventilation for fighting residential fires. It's kind of a unique application, especially if you think about the type of structures US has got. And then we have what I call societal trends. There are lots of things that are changing. What I call this is the changing in the fireground. Changing in the fuel loads, for example, changing in type of construction that people live in these days as versus in 1960s and 1970s. That makes a lot of difference in terms of the exposure firefighters get and the experience they get in these kind of fires. It's very different from what they've been trained on in many cases. Most recent projects are related to attic fires. And this attic fire project comes about because of the need for better insulation of homes. And one of the ways we insulate homes in the US is using polyurethane, polystyrene type of foam boards on the outside to provide better insulation. But it's also a significant fuel load. And now we are seeing some fairly, I wouldn't say large number, but we are seeing some increasing number of exterior fires that we've not seen before. And that's because of how we want to live. We want to live in an energy efficient society that makes changes in your construction that has some effect upon how firefighters have to react to those fires. So for today's discussion, I thought I'll select a few projects, and actually I decided that maybe I'll leave the ventilation project to the masterclass because there's a longer time available to discuss that in greater detail. But the 3 projects I want to talk about are somewhat unique because you may not think that some of them may be directly related to firefighter safety, but they are. First of them is related to commercial building safety, and I'll give a little bit of background as to how that came about. Second, we'll look at firefighter exposure to smoke particulates. And the third one is related to the change in how buildings are constructed in the US right now, using engineered products rather than solid wood products. I assume in Netherlands, lots of the houses are made out of wood structures, or no, they're concrete. Okay, so this particular may not be entirely related to what you're doing. But one thing you need to understand is that these changes in construction occurs irrespective of whether you're using wood or concrete or blocks. Especially when you're talking about facades, exterior, when you're talking about energy efficient insulations that you want to use. Windows change. If windows change, they break differently in fires than they used to, as you saw yesterday in one of the yesterday's presentation. And so there are considerations about construction that are important to the society out here also. This is a nice graphic that I like to use to show the various strategies that we have available for fire protection. Obviously, starting with education and prevention, materials, and its flammability detection alarm. One thing I like to make sure that I mention is that these are not sequential strategies. In other words, it's not you start from here and end up here. Once ignition starts, all of them are in play, so to speak, including your education, awareness of people to escape from a building. And the important thing is this is kind of a layered approach of fire protection that we use. Not any one strategy is very important, is dominant. All of them are really important in protecting property and life. And one of the things that we wanted to do was to see how codes and standards play a role in educating firefighters, especially their role in safety. The reason for that is that in many countries, as well as many jurisdictions in the US, fire service has the final authority for occupancy of buildings or major changes in the buildings. If that's the case, they need to understand what codes and standards. So building codes and product standards become very important from that perspective for them. So what we did is we wanted to use this technique, and I'll show you the technique in the next slide, by taking some examples of well-documented fires. And I have over the last 30 years, we've been collecting a large number of fire events around the world. It's actually a pretty large list. I've got fires going into 2013, and the list keeps on getting bigger, unfortunately. But some of the fires have been extremely well documented, and that's the ones we wanted to use because you can use that as an education piece. And what we wanted to find out from this, that if you were to take these various strategies that are available to us for fire protection, fire safety, how do codes and standards play a role when you look at any one of these different fire events? So we took one of the examples, the First Interstate Building fire in Los Angeles. It was a fire that we thought would never happen. It was a tall building fire, one of the more dangerous fires. And I think if you've seen one of those movies, Towering Infernos in the 1970s, a much older movie, it's actually like that type of a fire. You know, there were two big fires in the 80s, one in MGM Grand Hotel Plaza, Grand Hotel fire. That fire was more like the Towering Inferno fire, okay? Though it occurred 10 years or 12 years after this, after the movie came out. But this was a very dangerous fire because for various reasons. Number one, it was a very tall building, 62-floor building. In this particular case, sprinklers are just being installed in the building. It did not come pre-fitted, so it was retrofitted installation of sprinklers. And at that time, because of the construction work being done, the people who were monitoring the safety of the building were noticing a lot of nuisance alarms. And so at one point, when they started noticing nuisance alarms, they just ignored it. They reset the buttons and continued with the work until somebody from outside noticed there's smoke coming out of this place. And that's when they investigated, and the fire continued to grow for 5 floors, actually traveled through vertical openings, which kind of tells you there is some problem in the safety of this building because vertical openings are not protected. And in the firefighting efforts, communications were very badly hampered because of the concrete and steel in the building. Actually, firefighters got lost several times in the building as they were trying to find out who was where in the building. There was only one fatality, and the fatality was the person who went to the 12th floor to investigate what's going on, and when he opened the door, he actually entered the area of fire origin, and unfortunately perished. But it was a pretty large effort trying to fight the fire. For the first time, because of the tall building, there were helicopters in the air trying to give direction to the fire service as to what they were observing in the area. So we took this example to see how we can use this to develop a storyboard about how codes and standards work. And if you get a chance, you can go to our UL's website. There is a complete description of this fire, as well as, I think, 3 or 4 other fires that we investigated like this. But a storyboard consists of many pieces. One of the pieces is a nice graphic of the fire paths associated at a particular timeline. So we start from time 0, when the fire was detected, and you can progress through time. At various points in time, you can, through the documentation that's available, understand how the fire is progressing. You can then also, through looking up on various codes and standards, see what codes and standards are applicable at a particular time and place. So for example, at this particular time, about 11 minutes, you see there's a little bit of storyline. Smoke was present from 12 to 30. Detectors are activated. And once the detectors are activated, it's either used or it's compromised, because once it's activated, then obviously you don't have any more use for the smoke alarm system because it's done its job. But we didn't have any active fire suppression. The sprinklers were just being installed. They were not available for use. And all you were depending at that time was the passive fire resistance of the building and the fire service to mitigate the fire, to put out the fire. And then we can look at the various codes and standards to see how the codes and standards perform. Where was the gap? Now, in this particular case, we saw that there was smoke travel through vertical shafts. So clearly, there was a problem in terms of how the building was constructed. There was a problem in terms of fire alarm system. There was being reset. Somebody was not monitoring the fire alarm system and taking proper action when they saw that they're getting continuous alarms. So you can find out what went wrong and what went right in a particular fire event. And that becomes a really good storyline even for the fire service to understand how their action and reaction to these events helped or hindered the fire mitigation effort. As I said before, greater detail about this is available on our website. And actually, there are, I think, 4 or 5 different storyboards on the various fires that I mentioned. The second project that I like to explain, this was somewhat of a challenging project for many reasons, because, and explain to you, so there are several reasons why it was challenging. But it's to do with exposure of firefighters to the smoke particulates. And one would not think that's the major issue, but in fact, there have been several studies done now where it shows that when you accumulated smoke, whether in your turnout gear that you use and it's not cleaned regularly, or you have, for time, you have smoke deposited on your body, that could actually have some long-term health implications. So what we want to do is to provide data to the medical service community so that they can then develop cause and effect relationships. We obviously also want to provide guidelines to the first responders to make sure that they use the SCBAs during key elements of firefighting. Now, this is kind of important because in many cases in the US, when it comes to overhaul, firefighters feel that the air is good enough for us to go without our breathing apparatus. And I think that's a really dangerous thing, as we found out in this project. And obviously, we are going to work with NIOSH. NIOSH is a regulatory body in the US that protects fire service people and gives guidance on the protective equipment they should be wearing and the protocols for wearing the equipment. So one of the first motivation was a study by University of Cincinnati Medical School, where they did a study of 110,000 firefighters, not a small study. It's a pretty large study involving 110,000 firefighters in their firehouses. Now, in many cases, because you have to run the fire engines in the firehouses to keep them operational available, the diesel smoke can cause harm, and that's what they wanted to study. And they found that the smoke particles from diesel smoke can lead to generally elevated incidences of certain types of cancers, especially big organ cancers. And so this was one of the reasons why we wanted to study how what kind of particles, et cetera, we get from actual fires. We wanted to stay focused on particulates and gas effluents in residential structure fires because that's a primary fire ground for firefighters in most cases. Where are the potential exposures to fire service? It obviously comes from the fire ground exposures. Obviously, you have pre-entry, pre-attack. You do a knockdown. You go inside, actually, into the structure and fight the fire. And when you're doing active firefighting, you typically have the breathing apparatus. You're pretty much protected because of the breathing apparatus. But the real issue comes when you're in the overall phase. Many of the firefighters feel in the US that they don't need the breathing apparatus. It's clean enough for them to go because it's actually a burden on them. The big tank, the mask, etc. And then obviously we have some other routine emergencies that come up: car fires, dumpster fires, turnout gear. And the contamination is really another area of concern for us because if the gear is not cleaned regularly, then you are constantly getting in touch with the particles that will deposit on the gear. So this was a fairly collaborative research because there are many areas that we were not familiar with in this case. And so we worked with the Chicago Fire Department. We did our part in the lab scale. We can do a lot of materials level tests, lab scale tests. we worked with the Chicago Fire Department to actually do field experiments. And it's not an easy thing to carry very sensitive equipment into the field to do those experiments. But then we had to work with the University of Cincinnati Medical School for them to give us an understanding of what the data means. Because it's really a medical interpretation of the results, the chemical assay that we might be getting from the soot particles that may be important. And then CFD was involved in tactics because they had to suddenly change something based on the findings or not change anything if we do not find anything. And then we, obviously, as always, we try to broadly distribute our research through presentations after the project is completed. And some of the key measurements were typically what you do in fires, heat, release, smoke measurements. We also measured various toxicants, irritants, gases in the fire. I had to use some fairly sophisticated equipment to do this. In the lab, it's easy. You can use the techniques that are suitable to the lab. But you go in the field, you cannot take your gas analyzer. So we had to use an open path FTIR to identify gases in the fire plumes. And then we had to use a pretty sophisticated particle sizer to understand the size of particles because we felt that was an important aspect. And then analysis of particles deposited on firefighter clothing and equipment. And all these fires that are done in the lab were more what we call representative scale. In other words, they were real scale in terms of size. They were not scaled down sizes. And they had typical fuse you might find. For example, in an attic, there's generally a fair amount of storage. There is insulation. We did bedroom scenarios, outside decking scenarios, roof fires, kitchen fires, living room. We actually even did carbons. We bought second-hand cars from the dumpster and ignited them. It was somewhat of fun, a little bit exciting because you never realize that the bumper is going to explode on you because it's got the struts out there. And there was some unexpected excitement for us when you're doing the car fires. As you might have seen in actual practice, I suppose. But what was the find? In the room test that we did, I just highlighted a few of them. Carbon monoxide was fairly high even during the overhaul period. So that's kind of important thing is that you want to wear your breathing apparatus because CO levels could be generally very high. And obviously, if you get good ventilation, you can remove the CO, but that's part of the tactical plan that you might have. Okay. We also found that large number of particles in the overall were what you call invisible particles, less than 0.32 microns. Okay. 0.32 microns is a pretty tiny particle. You can't see it. Even when you have lots of those particles, you cannot see those particles. So it may look like it's clear when you're overhauling, but there are these particles that can come and deposit. You can breathe inside. So you have to make sure that you're wearing your breathing apparatus. The actual fire experiments were very challenging for us, partly because we had to train the firefighters to take our equipment with them. You know, we could not be there with them all the time, since they may have an event at 3 a.m. in the morning, for example, and we could not be there at 3 a.m. with them. So we had to train them. We had to provide gear for them so they can do the measurements during those events. And we had some very good candidates out here. This is Jim Dalton from the Chicago Fire Department. He actually got very experienced using an open path FTIR. So he could take the measurements of gases coming out from the fire. And that was very useful. So you can get a correlation between lab scale and field scale experiments. Now, this type of experiments are very useful for one big reason, is that if you want to go back and impact the fire service and show them that you got something important to tell, you want to show them that the experiments are done in the type of structures that they have to fight fires in. They're unlikely to believe us if we only do lab scale experiments. So the field scale experiments are very important for that reason. And then you see some of the gear that firefighters were wearing. Especially, we had trained quite a few firefighters to wear the various gas monitors, smoke particle analyzers, etc., that we would take afterwards and analyze the size, the gases that they had seen. This report is also available on our website if you're interested. It's fairly comprehensive in terms of the type of measurements we did. But the most important takeaway from is, I think there are two takeaways. One is that these ultrafine particles smaller than 0.3 microns, are significantly available during the overall phase, which many times not considered to be as serious a concern as the active firefighting, going and knocking under the fire. And that's important because then you have to wear your respiratory equipment even during the overall phase. Otherwise, there is a potential for a long-term. It's not a chronic, it's not a acute thing that you're not going to die right away from or have health problems immediately after exposure, but it's an accumulation thing. The finer the particles, the deeper they go into your lungs, and they settle there. You can't take them out, and they become irritants over a period of time, and then you develop respiratory problems, for example. So these are some of the things that we found not only in this study, but if you remember World Trade Center scenario where first responders were, I think about 400 to 500,000 first responders exposed to that smoke. And they're going through that phase because they had this long-term exposure to smoke as we're cleaning out the site. And they're being monitored with very similar effects that we might see in fire service. In general, in fire service, we found that certain levels of diseases are more prevalent than the general population. And this probably could be one of the areas. Now, obviously, one of the takeaways that the Chicago Fire Department took was to make sure that they have regular cleaning of their personal protective equipment so that they're not carrying and reaccumulating the dust that's collected on the gear. A third project is also related to I would say now it's very typically US problem, because it's related to change in how buildings are being constructed in the US. What we had found is that in the year 2000 onwards, we were hearing stories about firefighters going into a home structure and then falling through the floor into the basement. The reason for that is that the construction industry had gone away from using solid lumber that was typical construction method for floor assemblies to what you call engineered lumber. And here's what it looks like. So this is your typical, we call it a 2-inch by 10-inch. Turns out it's neither 2-inch nor 10-inch, but that's the trade size for this. It's a solid board that is used for constructing floor assemblies. So you have these beams, and you can put your floor on top of those beams. These have been replaced by engineered products. So it has the same strength as this, or maybe even stronger than this product. But then you can have cutouts available so you can put your ventilation ducts, etc., through it. It looks nice and tidy in your home, in your basement. And it's all very good because these products are I'd call them engineered green products. They use less wood material. They're just as strong. And that's where you have mass replacing your mass, which is actually a good thing. But what happens when they're exposed to fire? Exactly, yes. So what happens when they're exposed to fire? And when these trends occur in the industry, nobody asks the question, is who does it really impact? What is the chain of impact out here, right? And that's one of the questions that we wanted to address, because we're hearing the stories about near misses, firefighters almost falling or have fallen down and died in these kind of fires. And there are several incidents in tens, not in hundreds, in tens that are occurring. So we wanted to figure out for sure, get the data to understand and give firefighters training and awareness of what they should be doing. Now, this problem by itself is not the real cause. Okay, the other things that have changed that made fires grow much faster in the home. So the typical target time for fire service to come to your home once you have a dispatch is about 6 minutes. Okay, if you get flashover in 4 minutes, by the time the fire service comes to your home, it's already in post-flashover phase. Okay, so it's a serious fire or structured fire already. Okay, and therefore these collapses become more significant because they occur when the fire service comes to your home. He's trying to do search and rescue, and there is another fatality in that fire. So that's the importance of this project. And objectives, I stated them already. We wanted to make sure that we generate the data and then maybe have some improvements by changing the code system in the US. Have them recognize this an issue and provide some protection against it. So we did a series of tests we call lab scale tests, which uses standardized testing methodology. And one of the standardized testing methods is use a pretty large furnace that we have for fire resistance for floor systems. This is like a 4 meter by 4.5 meter furnace. and we expose it to flames at the bottom. I'll show you a video clip of that, and then see how the assembly behaves. And in this particular test, we had loaded the floor with load on the edges, as would be in a typical home, because you have your furniture, you have your refrigerator, etc. There's always towards the end of the perimeter of your floor system. And then you put 300-pound firefighters out here with full gear, approximately 300 pounds, so the weight down. Not real firefighters, they're dummies. So, right. I saw some concern in Ricardo's face. No, not real firefighters. Yeah. That's not the way to save firefighters, I think. Here's a video clip. So very quick, I won't go through the whole video clip because it's somewhat long. I could not clip it. But it shows you the furnace and the floor. This is the furnace underneath. You see the beams, these are engineered beams in this particular case. And you have the dummies on the top. And there's a view by IR camera on the top. This was part of the sub-objective for this project, to have firefighters understand what the infrared camera image actually shows you. And then you're looking at the two firefighter dummies on top and see how they, what happens to them. We found some very interesting results in this series of tests. These are, again, standardized fire resistance testing. So all it does is really gives you a reference point in comparing one type of system and another system. But we tested a 2x10 legacy. We call it the legacy because that's what was used in the early 80s and 70s. Without any sealing, we got about 18 minutes of performance. With a wood eye joist that you just saw, about 6 minutes. Lath and plaster is an old technique for floor and ceilings. Way back in the 1950s, you get about 80 minutes of performance out of that. So adding a barrier at the bottom makes a big difference in how it's going to perform. But the more common technique is to use gypsum wallboard. Gypsum wallboard is a fairly readily used construction material in the US for interior finish. But if you use gypsum wallboard, you can go from 18 minutes to 26 minutes. And for lightweight, which is your eye joist, you can go to about 20. Again, it provides additional protection. So a simple solution by having a half-inch gypsum wallboard, half-inch is 12 millimeter gypsum wallboard, can provide you an additional 20 minutes of protection, which is significant considering that fire service can get to your place in 6 minutes. It gives them another additional 20 minutes to do their search and rescue before they have to worry about having problems in collapse of the structure under them. The reason why it collapses is that the web part completely burns out. Remember, the web part is much thinner, and this math replaces mass, so you replace mass with engineering. But in fire, the web completely goes away in a short amount of time. Once you don't have a web, you don't have any strength left in the beam assembly. And that's one of the reasons why these systems fail so early into the fire test. One of the issues with this initial series of tests is that it only used a few different types of assemblies. And it was only limited to what we put in a furnace. So in addition to that, we decided that we'll look at various other assemblies, including some methods of protecting the wood with like intumescent coating or fire retardant coating. And we found that some of the coatings do help you a little bit. So you can increase your failure time by about 10 minutes or so if you put some kind of intumescent paint coating, which is getting to be very popular, but it's expensive. And we also found that there is a big difference between the new lumber that we have versus old lumber. We found an old home in Cleveland, and we got their lumber and created an assembly like this, and we got about 10 more minutes out of old lumber. So hard wood has better properties than soft wood. Okay, that's kind of interesting side benefit of doing this project. We did a fair amount of experiments with much larger spans that you find in today's homes in the US, because the furnaces are relatively small. Again, pretty significant fuel load. This is like a basement test. When you have basements, we can have fairly open areas. So these are pretty long. These are about 25-foot long spans. in this direction, and this is about 12 or 13 feet out in this direction. This uses what is known as an eye joist. And we ran several series of experiments in the lab and found fairly similar results in the performance of these kind of engineered systems. And then we were also very lucky to acquire some actual buildings that were being demolished because O'Hare, we have an expansion of O'Hare Airport in Chicago, and so some communities have been told to vacate. It turned out so timely for us that we found the structures available for us to do real scale tests. As I mentioned before, these scale tests, the field tests are always more expensive to do because of the instrumentation required, and to put the instrumentation in the field, you have to carry everything with you. Lab's such an easy environment for us to work in. But they're very important to provide a message to the fire service, because when they see these experiments and see the results, then they have far more confidence in the results that it is indeed applicable to their work. In the end, we were able to, after 2 years after research was completed, we were able to develop a code change that except for these few exceptions that are obviously a part of compromise we have to develop with the society, that we could use a 1/2 inch or a 5-inch, 1/2 inch gypsum wall board to protect your basements, to give you back about 20 more minutes of performance of your floor systems. And that protects the fire service. Okay, the last projects to do on ventilation. And I know that there is a long masterclass, so I'm not going to dwell too much upon this. But as in other projects that we've done with related to fire service, we always relied upon actual structures. Okay. And actual structures, and then we also go back into the field to do some experiments when we can. Now, typically, we've been very fortunate in many cases to find the structures actually that we can use. Because as you get renewal, urban renewal or rural renewal, in the small towns and cities, there are always some structures that are being demolished. And we have a good agreement with the fire service to identify those when you have these projects going. And then we can go out there and do these experiments and then repeat and try to make sure that we are getting the same results in the field as we're getting in the lab. Because that's one of the criticisms we get is, we did everything in the lab, how is it applicable to us? We have to work in the field. So that's a correlation we try to get. Some of the structures gives you the inside layout. Other important aspect of this test is we use actual fuel loads. So if it's kitchen, we actually design a kitchen. If it's a bedroom, we'll have bedroom furniture. And if you're doing 20 experiments, we'll try to buy all of the same type at the same time so that there is no variation. We can control the variation from test to test by controlling the materials that we're using in the fire test. And they're all done in the same structure. So we're able to get a good amount of repeat testing done. In every project we do with this, we always repeat a previous test we have done to make sure that we are not seeing something unusual. And these experiments require a fair amount of instrumentation. Instrumentation typically may include smoke alarms, smoke measurement system, velocity probes, temperature measurements. And in the lab, it's very easy to do all this. We can, in typical experiment like the 2-story structure, we may have about 400 instrumented data points in the structure in various areas. And then obviously we sometimes get very lucky. This was a pretty large acquisition of property for testing purposes. This is in New York. They were demolishing a series of townhomes. And this became available to us when we were doing the ventilation project. So we worked with the New York Fire Department. We worked with NIST, which is the National Institute of Standards and Technology. This is a science organization in the US. And collaborated with them to develop data on actual structures. And this is an interesting test because I've heard that when you use a hose stream, you can actually push the fire and cause the fire to travel in other parts. So we wanted to see if that's really true. Okay. So if I may explain, so you have on the rear end the doors open. The firemen are trying to. The fire is actually located in this area in here. You already have flashover. And they're waiting. They're going to put the hose stream there and trying to see if they can push the fire out. And what you see is that as you put your initial hose stream, you're obviously going to push some gases out, and that's what you see, those flames coming out. But as you continue with the hose stream to put the fire out, it's really not pushing the fire out. Actually, as you can see, it is really cooling, reducing the fire growth considerably. So the fire burden is considerably reduced by using the hose stream in this particular case. Important thing what we find is that it's really important to coordinate these activities between ventilation and fire suppression. And Bob James, I think, is going to discuss in greater detail later today. But ventilation is a big subject in the sense that it's so important for fire service to understand the dynamics change that occurs in ventilation. And that's why we spent last 3-4 years in studying ventilation, tactical ventilation that's used by the fire service. The most important thing is we need to obviously hear back from the fire service in terms of how our outreach is going. I mean, it's really, the research is very useful. Obviously, we think so. What does the fire service think? And on our website, if you go to, let's see, if you go to this website, fire.com/fire service, you will find all the projects we've done out here. In fact, I think there's a blog also. You can actually put your input here if you found something useful in our materials. There are a lot of training materials available already out here. So there are modules for each of the projects that tells you how the testing was conducted and what it means, how do you interpret the results, etc. So it's all for free. It's readily available. I like that word, free, 4-letter word, right? It's a good word, free. And it's all available. We also provide continuing education for fire service in the US using this training module. For the basic stuff that's out, there's no charge for them because they already paid us through the grant that we received from the government. So this is, and the Department of Homeland Security is very generous, and they said, yes, you must share this information with anybody else. They didn't want to restrict it only to the US Fire Service, because fire service around the world have the same problems. If you have more questions, obviously, you can contact me or Steve Kerber. Many of you already know Steve Kerber. He could have been here, but he has some experiments he's running. And so he had to be there for setting up those experiments next week. Be very happy to take questions if you have any, or there is time or no time.